Zero address allocation is a part of your stack processing. It simplifies that the absolute address of the operand is held in a special register that can be automatically incremented or decremented to the location on the top of the stack.
Now, what do you understand by zero address instruction? So, zero address instructions are basically those types of instruction that implies the absolute address. Now, the absolute address mainly it points to the address that is stored in the stack. And when the address is being stored in the stack, the address of the stack can be either incremented address or the decremented address, and it will be placed onto the top of the stack. Now, zero address instruction, the location of the operands are definitely implicit because you are not sure where the operands will be. Either they will be on the incremented side or on to the decremented side. For implicit reference, a processor register is used to term as accumulator. So here the accumulator is being renamed as AC and the processor register is used as a accumulator. For example, CMA, it complements the content of an accumulator. Now, instruction format design issue. So there were many issues which were existing with case of the design issue. An instruction consists of an opcode and one or more operand. It may be implicit or explicit. Opcode, we are aware that opcode is the signal that is either read or write, and one or more operand means whether we want the source and destination address, that is operand 1, operand 2, and so on. Each explicit operand is referenced using one of the addressing mode that is available into the machine. An instruction format is used to define the layout of bits allocated to these elements of instruction. So here you require the number of bits that are being typically allocated for executing the number of instructions that are there. Now, there are certain issues with this format. One is called as the length issue, instruction length, allocation of bit for different fields in an instruction, and variable length instruction. So what do you mean by instruction length? What is the size of the instruction? What is the length of the instruction? Allocation of bits for different fields. So what are the different bits that are being allocated in the field, and what is the variable length? The variable length is the length that can be increased or decreased simultaneously. It depends on the type of operations that needs to be performed, whether it's a read operation, write operation, or a read-write operation. The longer the instruction means more time of fetching an instruction, because when you say that the instruction is longer, it means that there is a possibility that there will be n number of other operators also executing onto the instruction. And there will be a dependency also, like in case of pipelining. If the instruction is designed in such a way that it contains LIFO, that is last in first out basis, then the time required for fetching will increase. For example, an instruction of an 32-bit of a machine with word size of 16-bit needs to memory fetch to bring the instruction. So even the memory parameter increases. So what are the desires that a programmer requires? More opcode. Opcode means whether it is a read or write operation, and more number of operands in an instruction, as it will reduce the length of the program. More addressing modes for greater flexibility in accessing various types of data. Now, what are the different factors that will decide what type of instructions to be used and what should be the length of instruction? First factor is called as the memory size. More bits are required in address field to access larger memory range. So more bits required simultaneously. Then you have the memory organization. If the system supports virtual memory, then memory range is larger than the physical memory. So it depends. If your system is supporting some external devices also, then definitely the possibility of dynamic memory increases because your system memory is considered to be a static memory. Hence, required the more number of address bits can be stored onto the system. Now you have the bus structure. The instruction length should be equal to data bus length, or it should be multiple of it. The instruction length should be equal to data bus length, like so that when we are storing the instruction, we can allocate the proper space for storing of the instruction also. The data transfer rate from memory should be equal to the processor speed. So when you're transferring a data from the memory, the processor speed should be placed on a very, very higher side so that the data transfer can take place very, very easily. More opcodes means more bits in the opcode field. Factors which are to be considered for addressing bits are number of addressing modes. More addressing mode, more bits will be required. If the number of more operands, more number of bits needed. If less operands, then less number of bits needed. Then you have register versus memory. If memory has more and more register can be used for operand reference, then fewer bits are required as the number of registers are far less than the memory size. The number of register sets. Assume that a machine A has 16 general purpose register and a register address requires 4 bits. However, if this 16 bits are divided into 2 groups, one of the 8 register, it will require 3 bits register addressing. Now, why 3 bits register addressing? Now, see, you have 16 general purpose register. Now you are dividing it into the form of 8 bits. 1 of 8 register. So why 3 bits are required? We are aware that the register works in the form of binary. So 2 raised to 3 is 8. So we require 3 bits of register addressing. Address range. The range of addresses that can be referenced is related to the number of bits, address bits. So when we say the range of address that can be referenced means the bits which has the source and also which has the destination. The source and the destination are being known. So we can have the address range. With displacement addressing, the range is opened up to the length of the address register. Address granularity. If a system with 32, 16 bit word, an address can reference a word or byte at the designer's choice. So if a system is of 16 bit or 32 bit or 64 bit or 128 bit, the designer has the choice to design the number of bytes that are being assigned with the system. And this is also referred as the address granularity. Then you have variable length instruction. Now, what do you understand by variable length? First of all, understand before coming into variable length whether your instruction is a static instruction or a dynamic instruction. If your instruction is a dynamic instruction, variable length comes into picture. Instead of looking at the fixed length instruction format, designers make choice to provide a variety of instruction formats. And these instruction formats can be of different size. It can be a 3-bit instruction format. It can be a 4-bit instruction format, 8-bit, 16-bit, and so on. Addressing can be more flexible with various combinations of register and memory references plus the addressing mode. So addressing can be more flexible. Like it contains the combination of the different addresses, different registers in memory, and the different types of addressing mode, whether it is a read addressing mode, write addressing mode, or a read-write addressing mode. Disadvantage, an increase in the complexity of the CPU, because as soon as the complexity of the CPU increases, definitely there is a possibility that the processing speed also increases and the output gets delayed. So this is the basic disadvantage when we increase the complexity of the CPU, because If the CPU has n number of ALUs allocated, n number of system buses, then CPU can withstand the complex instructions also. But at the same time, if CPU has a limited resources like limited ALU, limited system buses, then complexity in such cases increases to a very, very large extent.